Hi again. Now this is just embarrassing. All right. So the last thing I'm going to talk about today is smoothing or surface fairing. And again, what we're going to see is just by doing a simple change of variables, we're going to dramatically increase the effectiveness, in this case, the stability of our numerical scheme. And so the problem this time around, quite simply, is we have a surface like this bunny you've seen a couple times today, and we want to make it smoother. And we want to do this either because we have too much noise in our initial data or because we actually want to optimize the geometry itself. But as with all things in life, there are some challenges, and the biggest one probably is that if we try to smooth this thing out too quickly, then it's going to blow up. We get this numerical instability. And to add insult to injury, things are actually going to get even worse if we try to refine the mesh, because the maximum stable time step is related to the shortest edge length in our mesh. Another challenge is that depending on what kind of flow we have, we might get geometric artifacts that we don't like. For instance, here on the bunny, if we run a standard mean curvature flow, the ears pinch off into these sharp spindles. Additionally, the texture on our surface can get distorted by the flow, even if we run some kind of nice tangential smoothing along the way. The basic idea behind these fairing methods or these curvature flow methods is that to each surface we associate an energy E, and then we follow the gradient of this energy downhill, producing a series of progressively smoother and smoother surfaces. And most methods for surface fairing are based on just a couple different energies. One is the membrane energy, which tries to minimize the total area of the surface, and another is the Willmore energy, which tries to minimize the total mean curvature. If we take a linearized gradient flow of membrane energy, then we end up with the classic mean curvature flow. And if we do a linearized gradient flow on Willmore energy, we end up with bi-Laplacian flow. And if we write all this stuff out in terms of the Laplace operator, delta, then initially it kind of looks like we have some nice quadratic energies and some nice linear flows. But actually, don't be fooled. Something really important to understand here is that the Laplace operator itself is evolving with the surface. So in fact, these flows are extremely nonlinear, which means that even if we apply some nice implicit integration scheme like backward Euler, our time step is still going to be limited by the shortest edge in our mesh. And that's certainly going to be true if we want to do the full nonlinear version of Willmore flow as well. So rather than trying to improve the situation by using a fancier time integration scheme or doing some other linearization, something that's been sort of pursued pretty exhaustively at this point, we're going to take a very different approach, which is, again, my favorite thing, a change of variables. So instead of working with the position of the surface, we're going to work directly with its curvature. And the main practical payoff is that now the algorithm becomes incredibly stable. So we have this frog with all sorts of little bumps and creases and so forth, and in just 1, 2, 3 enormous time steps, it flows all the way to the perfectly round sphere. And something I should point out about this example is here I'm just using the most brain-dead time integration scheme imaginable. I'm using explicit forward Euler. So the stability here is not coming from some fancy integration scheme, but really results from our change of variables. If we watch this flow evolve, one other nice thing that happens is that geometric features are nicely preserved, so these ears stay nice and round. And you'll also notice that things like textures and displacement maps on the surface look very good. And the reason that happens has to do with the conformal nature of our flow, which I'll talk about in a bit. Likewise, if we watch the mesh itself evolve over the course of the flow, we'll see that the triangles preserve their shapes quite nicely. And this is important for preserving things like the numerical conditioning of the Laplace operator, which we can do without doing any kind of remeshing along the way. Okay, so to understand how this all works, it's actually a lot easier to look at the simpler case of flows on curves. And the beautiful thing about this story is everything I say is going to carry over directly to the case of surfaces. So we can think of any curve in the plane as the image of a map F from some interval on the real line, which basically gives us the position of the curve. And if kappa is the associated curvature, then a typical smoothness energy would just be something like the integral of curvature squared. And so if we then take a gradient flow, take the gradient of that energy with respect to position, that's our curvature flow. In the discrete case, this map F is just a sequence of vertex positions, F sub I, and the curvatures are just these exterior angles, kappa sub I. And so what this gradient flow is trying to do, essentially, is move these vertices such that the angles shrink as quickly as possible. And that doesn't sound too bad, except when you actually go and try to write out the flow equation explicitly in terms of these positions. And what you see is that curvature is an incredibly nonlinear function of position. So when you go and try to integrate this thing, especially with something like a numerical, implicit integrator, this is going to be a real problem. But just looking at this slide, you think, well, this is kind of bizarre what I'm doing. I have this very nice looking energy in terms of these angles or these curvatures kappa. Why am I trying to write everything down in terms of these positions F? Kind of strange. So a more natural thing would be just to write everything down in terms of these curvatures kappa. And now we get a nice quadratic energy and a nice linear flow equation. And so at the discrete level, what this means is that if we want to smooth out the curve, we can just shrink these angles kappa and then reconstruct the positions from those angles. So you can imagine we join edge vectors end to end using these new shrunken angles. Now, a really nice added bonus here is that we can naturally preserve the length of these edges because we get to pick what edges we use to reconstruct the curve. So why not pick them to have the same length as they did in the original curve? There's one problem we can run into, though, which is what if we have a closed loop? So now if we do something completely arbitrary to these angles, the curve may get smoother, but when we run this reconstruction procedure, there's no reason it should close back up. So we need to somehow understand what are the valid changes in curvature over time such that the curve stays closed. In other words, we need to develop some integrability conditions on curvature. If we go back to the smooth setting, we see that we have sort of two conditions to satisfy. One is that the endpoints should meet. And to keep this curve nice, we're also going to ask that the tangents meet at the endpoints. And the second condition is pretty easy to reformulate in terms of curvature. We just say, well, the tangents meeting at endpoints is the same as saying that the tangent rotates around a whole number of times as we walk along the curve. Or equivalently, the total curvature of the curve should be some integer multiple of 2 pi. So if we start out with a closed curve, we just need to make sure that the total change in curvature is 0 at any moment in time. This other condition is not quite as easy to reformulate in terms of curvature, but we work it out in the paper, and it ends up being, again, a very nice simple condition that says if we integrate the change in curvature against the position function, we get 0. Or another way we could write all this is to say this change in curvature, kappa dot, is L2 orthogonal to 3 fixed functions, the x-coordinate function, the y-coordinate function, and the constant function, which I'm writing as 1. So then our integration procedure looks like this. We start out with our desired flow direction, the gradient of this energy, and we just project out the components in the direction of these constraints. Then to get our new curvature, we start with our old curvature and take a little explicit forward Euler step. Okay? So here's a summary of the whole algorithm. We start out with our curve, we evaluate its curvature, we pick a flow direction, this very simple gradient direction. We then project out these constraint components, we take an explicit Euler step, and finally we recover the positions from the angles. And what you can see on the right here, I'm visualizing the edges in this curve as chain links to emphasize the fact that length is locally preserved quite well. In fact, we can check that as our time step goes to 0, the maximum length distortion goes to 0 quadratically. Okay, so now let's take a look at how this all works for surfaces. And as I mentioned earlier, the story is going to be essentially the same, except that now we have a different notion of curvature. In particular, we're going to work with a function rho, which controls the change in the surface curvature. So if you imagine that green values are positive and purple values are negative, then green spots are going to sort of bulge out and purple spots will bulge in. And more formally, what's going on here is that rho controls a change in a quantity called mean curvature half density, which I'm going to write as mu. Now, a really critical thing about mean curvature half density is that if you take its 2 norms squared, lo and behold, you get the classical Willmore energy. And so just like in the curve case, we get a nice quadratic energy whose gradient is really a nice linear flow. Another thing you notice about this flow equation is that it involves no spatial derivatives whatsoever. So what you can imagine, if you like, is that this is an ordinary differential equation evolving independently at each point of the surface. And this is really important from the perspective of numerical stability, because now it means our time step restriction has nothing to do with the mesh quality. The only thing we need to do is make sure that our time step tau is less than 1. So even if we have a really sort of terrible mesh like this one with lots of tiny sliver triangles, what we see is setting the time step just below 1 produces something stable, like in this top row. The surface rapidly flows to this round sphere. Whereas if we put the time step just above 1, things start to oscillate unstably, as you'd expect from forward Euler. So before I get too far ahead of myself, though, we still need to do a couple things to make this algorithm work. One is we need to figure out what are the constraints on curvature, just like in the curve case. And the other is we have to figure out how to recover the positions once we have the curvature. Actually, this second procedure, how to get the positions from curvature, is something we described in a paper at SIGGRAPH a couple years ago. And basically it boils down to solving two standard linear equations. But for the purpose of this talk, I'm just going to let that be a black box. So we have to solve a couple linear equations to get positions from curvature. And this is, a really nice black box, especially because people have already implemented this method and made their implementations available online. So if you're using C++ or MATLAB or CUDA, the sort of core component of our algorithm is already available. The most important thing to emphasize about this reconstruction procedure is that it's conformal, meaning as we go from our original surface to our newly reconstructed surface, we're going to nicely preserve angles. And that's why, for instance, the texture map looks so nice as the surface flows. Okay, so the one last thing we have to figure out is what are the integrability conditions? In other words, what are the conditions on the change in curvature that ensure the surface closes back up when we try to put it together again? And that's sort of the core thing we're doing in this paper. So these conditions are actually pretty involved to derive, and I'm not going to go through all that here, but I'll at least give you some basic motivation for what these conditions are and what they do. Our first condition looks very much like what we had in the curve case, which is that the total curvature has to be preserved, or in other words, the change in curvature has to be orthogonal to the constant function. Another constraint we need if we're dealing with surfaces of non-trivial topology is, well, we have to make sure that the surface closes up not just around small loops, but also around large loops that go around handles of the surface. And so for this, we compute some functions z that are related to the harmonic vector fields on this surface. And we ask that our flow direction be orthogonal to these functions. Here's an example of what happens without this constraint and with this constraint on the left. So on the right. So on the left, we compute this solution without this constraint and sort of force the surface to go back together in a least squares sense. And what you see is that doesn't work very well. We get this distortion of the texture and the geometry. Whereas on the right, the surface flows to this nice round torus. Another thing we have to deal with is things called sphere inversions. So in three-dimensional space, there are these transformations that preserve angle and preserve Willmore energy, so both of the things that we're trying to preserve in our flow, but they can severely distort area, which is something that we don't like. For instance, this little cube down here gets very stretched out on one side and very compressed on the other. And to avoid these kinds of motions, all we have to do is ask that our flow direction be orthogonal to the three components of the normal function. Okay? So again, we have all these nice linear constraints. Here's an example of, again, what happens if we do and don't use the constraint. So on the top, we ignore this constraint, and you can see that this coffee cup flows into this sort of chocolate croissant, where the area gets shrunk on one side. And on the bottom, it flows to a nice chocolate donut that's perfectly round and has a nice area distribution. Another thing we can do with our flow is we can apply filters to this gradient direction to get different appearances. So here I've applied a few different frequency space filters to emphasize different features in this bunny. And this kind of filtering is especially important because it lets us emulate the behavior of traditional Willmore flow, position-based Willmore flow, in this curvature metric, or in this conformal case. And so what I've done here is I've taken this bumpy surface on the left and applied a filtered gradient flow in the middle, this conformal flow, and you can see what we get looks nearly identical to what you get using standard position-based Willmore flow. Okay, so let's just do a little bit of evaluation of the method. Actually, I just want to look at two things. One is, let's see what happens as we refine our time step. And just like in the curve case, what you see is now our angle distortion vanishes as the time step goes to 0, although this time we just get linear convergence. More importantly, perhaps, is how does the method compare in the real world against all these other methods for surface fairing? There are a lot that have been developed over the years. And so what I've done here is I've gone out, I've implemented all these different methods, and I've run them each for 10 seconds of CPU time at the maximum stable time step. So I'm really pushing these things as hard as I possibly can. And what you see is that even though some of these methods are very, very cheap to evaluate for a single time step, they really don't make much progress. So the problem is that even if for a method that's very cheap, you have this very severe time step restriction that has to do with the quality of your mesh. And in fact, in this example, I'm using a very, very nice mesh. Most of the triangles in this bunny are equilateral, like you saw in this movie at the beginning. And even then, these methods don't make much progress despite being very cheap per time step. In fact, the only method that manages to get to a sphere, the only other method that manages to get to a sphere after 10 seconds is the modified mean curvature flow of Misha over here. And so that's a really nice method, although in this context it has a couple of drawbacks. One is that it can exhibit pretty significant conformal distortion in intermediate stages of the flow. And the other is sometimes you still get these sort of sharp geometric artifacts like in the ears of the bunny. And in contrast, here's what we get with our method. So these ears stay nice and round, and we get low conformal distortion throughout the flow. I guess the other thing to point out here is that our method works for surfaces with non-trivial topology. Okay, so in conclusion, what we did is we took this traditionally very challenging problem of Willmore flow, a very high-order PDE, and we turned it into a simple linear ODE by just working with the curvatures instead of the positions. The practical outcome is that we're able to take very large time steps, and we preserve geometric features quite nicely, as well as any textures associated with the mesh. From an implementation point of view, although I didn't talk a lot about it, we're just solving sparse linear algebra problems. So again, you could just throw this into your favorite solver, parallel solver, whatever you like. I also want to point out that all this machinery we've developed about these integrability conditions is useful not just for curvature flow, but it's a general theory that applies to any kind of surface deformation you might want to do. So for instance, if you want to do shape interpolation, conformal shape interpolation, you can apply the same tools and get the same kinds of results. Also, in the paper, we describe how to very efficiently develop or generate constant mean curvature surfaces like this thing you see on the right here by just setting appropriate boundary conditions. And finally, I should mention, if you really are interested in this stuff and want to learn more, I've written about it in great detail in my thesis. I have all sorts of nice explanatory figures and calculations and so forth that you can look at to learn this stuff. And that's it. Thanks for your attention.
Questions? Should be some.
Will this generalize to TET meshes in 3D?
Yeah, you know, it's funny. When I gave this talk about this other paper a couple of years ago, somebody asked the same question. Can you do these conformal deformations with TET meshes? And the issue is that in 3 dimensions, there are no interesting conformal deformations. All you have are things called Mobius transformations, which are very, very rigid. And so in terms of exactly preserving angles, you really can't do something like a curvature flow. But you know, then the question is, can you redefine the problem you're solving rather than saying I want to exactly preserve angles? Can you come up with some other definition that makes this machinery work? And that's an interesting question.
Thank you.
Hi, I got a quick question about the time integration. So you mentioned that the method is already incredibly stable using explicit method, right? So do you gain anything to go to implicit method? And second question is about the choose of time steps. Let's say today your total target of time step is 10, And does it make a difference if you choose, let's say, 5 steps of step set 2 and 2 steps of step set 5?
Right.
And so that would
Yep.
be a quick question.
Both great questions. So in terms of implicit integration, this is something you might try out in the curve case. That could be interesting. In the case of surfaces, I think it would be challenging because this reconstruction procedure is an eigenvalue problem, and so you'd be sticking an eigenvalue problem into your implicit integrator. I don't think that's, that's not something I know how to do. But yeah, maybe worth thinking about. In terms of the choice of time step, as always, the choice of time step will affect the accuracy. So even though the method's very stable, you can take enormous time steps. As usual, the bigger your time step is, the less accurate your solution is. And the way that this maybe shows up in these flows is that if you take time steps that are too big, you might miss out on things like smoothing out of high-frequency details. Now, from a practical perspective, maybe that's not a big deal because you could, in conjunction with this nice stable flow, run some sort of local smoothing to get rid of these high-frequency details. But yeah, the general guidance is smaller time step, more accurate.
Okay, thank you. Thank you, all the presenters. Very fine session.
Thank you.